When selecting a refrigerant, many factors influence the decision. It is important to remember that no refrigerant is perfect. One might have wonderful thermodynamic properties, but is highly flammable. Another refrigerant may be safe for humans to handle, but negatively impacts the environment. Selecting a refrigerant for a specific application involves a careful consideration of the following factors: operating pressures, operating temperatures, equipment selection, cost and availability, safety and handling, environmental concerns and regulations. One factor that affects refrigerant selection is operating pressures. All other things being equal, a good refrigerant will have a low condensing pressure and a high evaporator pressure. A low condensing pressure is preferred because higher pressures typically require more compressor horsepower. Furthermore, compressed gases are inherently dangerous because a leak could physically injure someone, even if the refrigerant is non-toxic. Additionally, operating at high pressures require equipment, piping, and appurtenances to be designed for that pressure, which increases the cost of equipment. When considering the evaporator pressure, a higher pressure is advantageous. Specifically, it is ideal if the evaporator pressure is above atmospheric pressure, or 0 psig. When the pressure is above atmospheric pressure, a leak will cause refrigerant to escape the system, which can be detected and corrected. When a system operates below atmospheric pressure, which we call a vacuum, leaks will result in air being sucked into the system. Air that leaks into a system is a non-condensable gas that negatively affects the system in a variety of ways. First, the air that leaks into the system will increase the total pressure of the system, which result in higher compressor ratios, increased compressor power consumption, and higher discharge temperatures. Second, air typically has some water vapor in it which will condense and collect in the evaporators. The water can even freeze in systems with extremely low evaporator temperatures. Sometimes, the water will even react with a halocarbon refrigerant to form new acidic compounds, which can damage a system. Ammonia systems can handle water better than halocarbon systems, but measures must be taken to limit air leaking into any refrigeration system. The table below compares the condensing and evaporator pressures for several common refrigerants. As you can see from the table, carbon dioxide R744 stands out because of its high pressures. Most refrigerants have maximum condensing pressures between 100 to 300 psia. The operating temperature is another refrigerant selection factor that must be considered. Extreme temperatures can require specifically designed equipment. Furthermore, personal safety is also a concern, as skin burns and frostbite are both potential risks if a pipe or equipment is accidentally touched. On the low temperature side, equipment must be designed for the lowest possible temperature that the system will operate. On a pressure vessel data report, or U1 form, this is listed as the minimum design metal temperature, or MDMT. Most vessels in an ammonia refrigeration system are rated for negative 20 degrees Fahrenheit at the corresponding maximum allowable working pressure, or MAWP. For temperatures lower than negative 20 degrees Fahrenheit, the design engineer would be responsible for ensuring the equipment is properly rated. The temperature in any refrigeration system is highest at the outlet of the compressor. This temperature is referred to as the discharge temperature. As the compression process occurs, heat energy is added to the refrigerant vapor. This heat is commonly referred to as the heat of compression. The theoretical discharge temperature can be calculated by using the principles of thermodynamics.
All right, in this example, I'm going to demonstrate how to calculate the theoretical discharge temperature for a given refrigerant. So let's say we have an ammonia system, it's R717, that's operating with a suction temperature of 10 degrees Fahrenheit and a condensing temperature of 95 degrees Fahrenheit. How do we calculate what the theoretical discharge temperature might be? And I'm going to walk you through these steps. I'll warn you in advance, this is a bit complicated, and the purpose of this video isn't so much that you would be able to repeat the exact steps for any refrigerant. Probably you need to take a thermodynamics course to really get in depth, but this will at least show you how the various characteristics of the system or the operating parameters of the system affect the discharge temperature. The first thing I need to say is that we assume in the theoretical discharge temperature that the compression process, the process of the vapor entering the compressor and exiting up to discharge pressure, is isentropic. That means it's constant entropy. Okay, that actually isn't true. It isn't constant entropy, but that it is a theoretical discharge temperature. So that would be the best case scenario. And so what we do is we're going to, at the suction temperature, determine what is the entropy of the vapor entering the compressor.
Entropy can be a difficult concept to understand. In the context of thermodynamics, entropy can be thought of as a measure of disorder. The second law of thermodynamics teaches that entropy always increases over time. In the refrigeration cycle, entropy is used to determine the theoretical discharge temperature. The term theoretical is applied because we assume the compression process to be isentropic, which means constant entropy. In reality, entropy always increases, so the theoretical discharge temperature calculation represents an ideal scenario that is never true in the real world.
Okay? And you could do that through a variety of sources. I've kind of chosen to use the ASHRAE Fundamentals book. I have one page of that printed out here in my hand, and I'm simply going to look up in this far left column 10 degrees Fahrenheit and determine what the entropy of the ammonia vapor is. Now you must beware because they'll give the entropy of the liquid and the entropy of the vapor. But since we're looking at the entropy of the vapor entering the compressor, it's important that we use vapor. And I can see here that the vapor entering the compressor, entropy was often using S, or an S for entropy. The V subscript indicating this for the vapor is 1.31496. Okay, and that is, the units are BTUs per pound degrees Fahrenheit, which happens to be the same as the units for specific heat. Okay, so that's the entropy of the vapor entering the compressor. Now, I just told you that we assume in the theoretical discharge temperature that it's an isentropic process, which means that the entropy, I'll call this V1, which means that the entropy of the vapor exiting the compressor is going to be the same as that entropy. So that is the same value, 1.31496 BTUs per pound degree Fahrenheit. We had no change because it's an isentropic process. However, we know that the saturated condensing temperature is 95. So this is our key. So now, because the vapor leaving the condenser or leaving the compressor is not saturated but is superheated, I can't use the same chart anymore because this is the saturated table. So instead, we need to find the superheated tables for ammonia. And these are a little bit more difficult to find than the saturated tables, which are pretty readily available. However, they're not too hard to find. A quick internet search found me the superheated table I needed. IIAR in the ammonia data book has the superheated tables printed, and you might have these references available to you. And basically what you do is I'm going to go to find the saturated temperature in our case, that's 95 degrees of condensing. And there's a column that lists entropies and the corresponding temperature that goes with those entropies. And I'm going to find the value that most closely matches what we believe the entropy to be, which is 1.31496. Okay, and looking at this table, I find there at 220 degrees, the entropy is 1.320, slightly different than this, but close enough for our purposes, which tells me that the superheated or the theoretical discharge temperature is approximately 220 degrees Fahrenheit. Okay, approximately. I could get, because those numbers didn't align perfectly, to really dial it in precisely, we could interpolate between data here, but that's unnecessary.
When looking up information in a saturated or superheated table, sometimes the reference values fall between two rows in the table. When this occurs, engineers must either approximate the value or interpolate between two available rows. In thermodynamics, interpolation is a way to fill in the holes in tables. For example, in this saturated table, the thermodynamic properties for ammonia at 15 and 20 degrees Fahrenheit are displayed. But what if we desire to know the pressure of ammonia at 17.5 degrees Fahrenheit? Since that is not a row in the table, we could either approximate the pressure by using the closest value, or we could interpolate between the 15 degree Fahrenheit and 20 degree Fahrenheit rows. Since 17.5 is the average of 15 and 20, we can interpolate that the pressure at 17.5 degrees Fahrenheit would be 45.660 psia, which is the average of the pressures corresponding to 15 degrees and 20 degrees. Mathematically, interpolation is more complicated when the desired value is not halfway between 2 points on a table. But linear interpolation can be used with the application of simple algebra and what we know about the slope of a line. When using linear interpolation, we assume that a straight line connects the distance between 2 points. Then, applying simple math allows us to approximate the value of a data point that lies on the line. To save time, in the remainder of this video, we'll estimate refrigerant properties using the closest available data in the table.
Now let's compare ammonia's theoretical discharge temperature, 220 degrees, which happens to be fairly hot. By the way, before we compare it to R22, which is what we're going to do, I would like to point out that the actual discharge temperature happens to be lower typically, and that's due to oil cooling that takes place, and the external oil cooling through thermosiphon oil cooling or water cooling, or the water-cooled heads on reciprocating compressors. So I'm going to draw a line here. Let's just copy these steps for R22, kind of historically one of the main synthetic alternatives to ammonia. We're going to go with the exact same operating parameters. I'm going to grab my notes here so I can do this quickly. And we look at those same exact parameters. The entropy is 0.22625 BTUs per pound degree Fahrenheit. All right. Again, same operating parameters. I won't rewrite that. That's the entropy of the vapor entering an R22 compressor. Entropy of the vapor exiting is going to be the same. So I'm going to repeat my steps using the superheated table now for R22, which I am holding here and I got from, I believe, the DuPont website. Again, pretty readily available, not too hard to find this. And looking up the value that corresponds to 95 degrees, the 95 degree Fahrenheit table, I can find my entropy and match it up with what the temperature is expected to be. And the answer is 140 degrees Fahrenheit. The theoretical discharge temperature of an R22 system compared to an ammonia system with identical parameters for suction and condensing temperature is 80 degrees less, meaning all other things being equal, if we're just examining theoretical discharge temperature, R22 is superior to ammonia in this example.
The actual discharge temperature is generally lower than the theoretical discharge temperature. This is because most compressors have an oil cooling system that removes some of the heat of compression. Reciprocating compressors are typically cooled by circulating water, which cools the cylinder heads. Screw compressors utilize much more oil than reciprocating compressors. In addition to lubricating the compressor, the oil also absorbs much of the heat of compression that then is removed by an oil cooling system. Therefore, the theoretical discharge temperature represents a worst-case scenario and can be used as a design constraint. When comparing refrigerants, a low discharge temperature is preferred. High discharge temperatures tend to break down the compressor oil, which can result in the formation of sludge and other harmful compounds, and increase maintenance costs due to wear and tear. The theoretical discharge temperature can be lowered by reducing the condensing pressure or increasing the evaporator pressure. Care should be taken to avoid supplying a compressor with superheated vapor. As a rough estimate, for every degree Fahrenheit that the temperature is above saturation, the theoretical discharge temperature will be 1 degree higher. Insulating suction pipes is one helpful way to avoid unnecessary heat being absorbed into the refrigerant downstream of an evaporator.
All right, now let's take our original example, which we already calculated the theoretical discharge temperature, and we're gonna manipulate our operating parameters. So instead of 10 and 95 degrees Fahrenheit, we've changed our suction temperature to 30 degrees Fahrenheit, increased it by 20 degrees, and reduced our condensing temperature by 5 degrees Fahrenheit, down to 90. So how does that affect theoretical discharge temperature? Hopefully, intuitively, you have a bit of a sense that this will decrease it, but let's show how that gets determined. And really, it's just a repeat of the step we did earlier. We're going to go to the suction vapor entering the compressor and look up the entropy. And it turns out for these conditions at 30 degrees Fahrenheit for ammonia, it's 1.27842. Units are BTUs per pound degree Fahrenheit. All right. The actual number for the entropy is not meaningful to us. The point is, it's an isentropic process. We need that entropy exiting the compressor will be the same as the entropy entering the compressor, and we can use that by referring to the superheated tables. But this time, instead of going to the 95 degree table, we're going to go to the 90 degree table. And when I look at the 90 degree table, which I'm holding here, or here actually, which I'm holding here, I learned that this has reduced our theoretical discharge temperature all the way down to 170 degrees Fahrenheit, which is substantial, right? So we went from 220, I guess I should do an approximate too, because I'm not really interpolating between columns or rows in the table, but we've reduced our discharge temperature by approximately 50 degrees. This is a huge advantage to us, right? If you're operating a system, it's heat, it's friction, it's wear and tear on equipment, which is not good. So by increasing our suction temperature and by decreasing our condensing temperature, we were able to reduce this substantially. Now, let's see what happens if we do a third example where we keep our 90, but we'll lower our suction temperature. Circumstances have changed. We need to cool product a little lower. Now we're going to lower our suction temperature all the way down to 20 degrees. So it's in between the first and second example. Okay, so what does this do? Well, this makes and you can probably guess our entropy is going to be somewhere between this number and this number, about halfway in between. Our entropy becomes, so we're still going with the 90 degree Fahrenheit condensing temperature. Our entropy is now 1.29629. Write the units. And this results now in a theoretical discharge temperature of 190 degrees. I can grab that from I was able to determine that by looking at this entropy on the superheated table corresponding to 90 degrees Fahrenheit. So what's the takeaway? The takeaway is that as suction temperature decreases, discharge temperature increases. And as condensing temperature increases, discharge temperature increases.
The tables below compare the theoretical discharge temperature for several common refrigerants at the same operating temperatures. Ammonia is the least attractive when viewed from this single lens. Now let's look at the theoretical discharge temperatures for a few of these refrigerants at a lower evaporator temperature. Notice that in each case, the theoretical discharge temperature increased as the evaporator temperature decreased. Ammonia is nearing 300 degrees Fahrenheit, which is an unacceptably high temperature. Refrigeration engineers work around this restraint by utilizing a two-stage system, which is beyond the scope of this video. The choice of refrigerant has a direct impact on the equipment needed to operate the system. Each refrigerant has a unique density that affects the size of pipes and equipment that are used. Density is defined as the pounds of a substance that can fit in 1 cubic foot. The density of a given refrigerant will change depending on the temperature and pressure of the refrigerant. Furthermore, vapor has a much lower density than liquid, meaning the same pound occupies much more space. So how does this affect equipment selection? There are 2 primary characteristics to consider. The first is called the refrigeration effect and is the amount of heat, typically measured in BTUs, that each pound of refrigerant can absorb in an evaporator. When comparing refrigerants, a higher refrigeration effect is preferable. At 10 degrees Fahrenheit evaporator temperature and 95 degrees Fahrenheit condensing temperature, the refrigeration effect of ammonia is 463 BTUs per pound. R22, which historically has been one of ammonia's key competitors, has a refrigeration effect of 67.7 BTUs per pound at the same conditions. This means that each pound of ammonia can absorb 6.8 times the amount of heat absorbed by a pound of R22. When comparing the refrigeration effect, ammonia is far superior to R22.
Okay, now let's take our original system, that ammonia system that was operating at a 10 degree suction and a 95 degree condensing temperature, and let's calculate its refrigeration effect, all right? Well, how do we do that? I've drawn here depicted a real simplistic Moliere chart or pH diagram. No need to fret if you're not familiar with those, or I'm not going to get into detail about those. It's a bit more advanced topic, but I've kind of diagrammed a basic refrigeration cycle on this pH diagram. First of all, we have pressure on the vertical axis, and we have enthalpy on our horizontal axis. So our units down here would be BTUs per pound. Our units here, of course, are PSIG, which I've shown. I've kind of shown this system depicted on there simplistically. So the pressure, this horizontal line here represents right here at point number 1, the vapor entering the compressor. This is our isentropic compression up to the discharge pressure. A constant pressure condensing process at 181.21 psi, which happens to correspond to the 95 degrees Fahrenheit. And then this line from here to here represents the expansion, travel of the refrigerant through the expansion valve down to the suction temperature of 10 degrees Fahrenheit, which corresponds to 23.87 or 787 PSIG. So that's all depicted there. The refrigerating effect is the amount of BTUs per pound that can be absorbed in the evaporator, and it's represented by this line between points number 4 and point number 1. So it's not too difficult to calculate. I've told you that point 1 represents the vapor entering the compressor. So I can look up what the enthalpy of the vapor is entering the compressor by using any saturated refrigerant table from a thermodynamics book or the ASHRAE fundamentals book. I have page 30.41 of ASHRAE fundamentals printed out here, and that's what I'm going to use in this example. So at this point, we have a saturated vapor because it sits right on the dome, the right dome of the pH diagram, and I can look up at this temperature of 10 degrees Fahrenheit and see that the enthalpy of the vapor is 614. And some change. Question is, what is the enthalpy here? Because then that's just a subtraction problem. This does not fit perfectly on our dome, so I can't look up that value easily. But since we assume the process of going from our high pressure liquid down to the low pressure liquid to be isenthalpic or a constant enthalpy process, we can go to point number 3 and determine what the enthalpy is, because the enthalpy at 4 is exactly the same. That's a perfectly vertical line, theoretically. So if we go to our 95 degrees Fahrenheit, which corresponds to 181 psig, look up the enthalpy of the liquid. So this is the enthalpy of the vapor at 10 degrees. Now let's get the enthalpy of the liquid at 95 degrees. And that, again, just looking at the table here, 95 degrees, enthalpy of the liquid, I am looking up and finding it to be 149.241. Okay, so our refrigerating effect is the difference between that enthalpy and that enthalpy, or subtracting these two numbers. And it so happens with a calculator, I can easily do that math problem. 614.669 minus 149.241, and that equals 465. So our delta H, which is our refrigeration effect, is 465.428 BTUs per pound. So what does that mean? That means for every pound of ammonia in our evaporator has the potential to absorb 465.4 BTUs per pound. So that is how we calculate the refrigeration effect. Now let's compare that to R22 in the exact same conditions. Okay, R22, I would repeat the exact same steps that I just did. Same pressures, same temperatures, different pressures. The only difference is I have to look on a different table, but I'll follow the exact same steps. It turns out for R22, the refrigerating effect will be the difference between the enthalpy of the vapor at 10 degrees, which is 105.580. That's the enthalpy of the vapor, 10 degrees. Now the enthalpy of the liquid at 95 degrees. So the enthalpy of the enthalpy of the liquid at 95 degrees Fahrenheit is 37.938. Ran a little tight on space, but you can see here, that means that delta H, or our refrigeration effect for the R22, is going to be the difference between these two numbers. Again, plugging into the calculator will give us this answer. I'm right below here is 67.642, and that's with the units BTUs per pound. So a magnitude difference, right? What does that mean? It means when comparing the refrigerant on a mass basis, it's important, on a mass basis, ammonia is far superior than R22 in its ability to absorb BTUs in an evaporator in these operating conditions.
Refrigeration effect only tells part of the story. Each refrigerant has a different specific volume, which is defined as the number of cubic feet required to hold a single pound. Compressors are constrained by the volume of the gas that they can compress. In other words, they don't care how many pounds per minute are required. Instead, they are capable of compressing a specific cubic feet per minute, or CFM. The second characteristic of a refrigerant that must be considered when selecting equipment is the volumetric flow rate measured in CFM per ton of refrigeration. At 10 degrees Fahrenheit, ammonia vapor has a specific volume of 7.32 cubic feet per pound, compared to a 1.15 cubic feet per pound for R22. This means that 1 pound of R22 vapor only needs 16% of the space required for 1 pound of ammonia vapor at 10 degrees Fahrenheit. So why does this matter? Because compressors are designed to compress a fixed volume, if we do a little math, we can prove that at 10 degrees Fahrenheit evaporator temperature and 95 degrees Fahrenheit condensing temperature, the required volumetric flow rate of ammonia is 3.15 CFM per ton of refrigeration, compared to 3.39 CFM per ton of refrigeration for R22. In summary, relative to equipment selection, ammonia and R22 are nearly equivalent.
So last time we looked at comparing the refrigerating effect between ammonia and R22, and we demonstrated that ammonia is superior to R22, a magnitude difference. However, that really doesn't tell the whole story, because equipment is sized not on a mass basis, but more on a volume basis, like how much space is taken up by the refrigerant. So this gets us partway to what we want to know, but now let's find out how many cubic feet are needed to do the refrigeration that we want to do. So in order to do that, first we're going to calculate the mass flow rate for ammonia, the same original operating conditions, what the mass flow rate in pounds per minute would need to be in order to achieve 1 ton of refrigeration. I just picked 1 as an arbitrary number. It's nice simple math. So to do that, I'm gonna say that we're gonna go back to like our latent heat equation, which is Q equals M delta H. Okay. Notice I put a dot over both of those. Kind of convention, if you put a dot over a characteristic, it kind of makes it instead of mass, it's now a rate of mass. So this is now pounds per minute instead of just pounds. Instead of this being BTUs, is BTUs per minute or per hour or some unit of rate. We want to calculate this mass flow rate, so we will rearrange our equation by dividing both sides by delta H, which will isolate m dot by itself, and m dot will equal q dot over delta H. We know our delta H because we already calculated that for ammonia right here. So we already have that value. The q dot would be our rate of heat transfer, and I just told you that's going to be 1 ton of refrigeration. You might recall from previous lessons, 1 ton of refrigeration is equivalent to 200 BTUs per minute. So those are equivalent. Those are equivalent right there. It's like saying 1 foot equals 12 inches. There's no difference. So now we just got to do a little bit of math. We think m dot equals, and we have our 200 BTUs per minute. We're going to divide that by our delta H that we alrede calculated, which is 465.428. That's BTUs per pound. Our BTUs are going to cancel, we'll end up with pounds per minute, and the answer is it takes 0.43 pounds per minute, and that would be per ton of refrigeration. So we would need that mass flow rate for every, if we were to for every ton of refrigeration we need out of our system. If we repeat these calculators for R22, all we need to do is plug in 67.642 instead of this number, and I have that calculated here for R22, and it happens to be 2.95. So this is for, I'll almost put 717, that's for ammonia. The equivalent m dot for R22 is 2.95, is that what I said? Yes, it's 2.95. So this is simply demonstrating the same thing we already knew, that ammonia is superior to R22 when looking at it from a mass basis. But I kind of gave a hint early on in this video that when we size pipes and we size compressors and we size vessels, it's not on a mass basis, it's on a volume basis. How much volume do we need to hold this refrigerant to do what we need to do? So in order to convert this and look at it from a volume basis, we now need to look at what is the specific volume. Just a brief reminder, specific volume is the cubic feet, units of this is the cubic feet needed to hold a pound of the refrigerant at some condition, right? So we can look up from our saturation tables what is the specific volume for ammonia at 10 degrees Fahrenheit, our evaporating temperature. The specific volume for ammonia, B717, I'll say, that's for the ammonia's refrigerant number, is 7.3020. Okay. So if we were to multiply now to get our CFM, our volume flow rate is going to equal the multiplication of this, of our specific volume, 7.302 feet cubed per pound. And we're going to multiply that times our mass flow rate, which is 0.43 pounds per minute. You can see here the pounds will cancel, and we'll be left with feet cubed over minutes, or in other words, more commonly said, CFM. And the resulting CFM is 3.14 CFM. And again, that is per ton of refrigeration for a single ton. So what does it look like for R22? Going to follow the exact same steps. The difference is the specific volume is different. It so happens R22's specific volume, I'm running out of space here a little bit, but I'll write it down low here. R22 specific volume, B22, equals 1.1276. So we repeat these steps and we multiply 1.1276, which is what we did there, multiplied by our MDOT for R22, which is 2.95. I'll write it so you can see it. This is the CFM for 717. Now here's our CFM for 22. It's going to equal 0.1276 feet cubed per pound. I'm going to multiply that. I'm going to multiply that times 2.95. I'm totally running out of space, but that's okay because I'm just about done. And the resulting answer here is 3.33 CFM. So when it's all said and done, on a volume basis, ammonia is still better, but marginally better. It's actually very close, 3.14 compared to 3.33, not a noticeable difference. So what does that mean? That means while you will need quite a bit more pounds of R22 compared to ammonia, when sizing pipe and equipment, which is on a volume basis, they're pretty much the same. Very similar size pipes and equipment that you'll be using, whether it's R22. And the size really affects the cost of installation and so forth. So hopefully that's helpful to demonstrate how this is calculated.
Silver is the most conductive metal available and better than copper in many ways. Then why aren't electric wires made of silver? The answer is simple, because silver carries a hefty price tag. Most applications settle for copper as a suitable alternative. In the same way, one refrigerant may have superior thermodynamic properties compared to another, but if it is too expensive, it may be cost prohibitive for a project budget and another refrigerant will be selected. Availability is another selection factor. If a refrigerant is hard to get your hands on, it may be an unacceptable risk since recharging a system quickly after a leak is often a high priority. For example, Since many halocarbons are in the process of being phased out, their availability in the future is a real concern. When a refrigerant is banned due to environmental concern, only reclaimed refrigerant may be available. When this occurs, it impacts both the cost and availability of the refrigerant. Safety and handling are important considerations when selecting a refrigerant. Some questions that should be asked are, what are the permissible exposure limits? Is it flammable? Will it react with other substances at the site if it leaks? How does it affect humans? Are special first aid measures required? What does it look and smell like? Are there technicians available to work on systems using it? No one answer is a definite deal breaker, but the collective answers all factor into a good decision. The location of the site where the system will be used may add weight to the importance of a single question.
So people select refrigerants for a whole variety of factors. Really, there isn't one way they go about it. And unfortunately, they're not always selected in the best manner. Just like anything else in life, a lot of times people just pick what they're used to. Maybe they're used to working with freons, so they're going to keep working with freons, or they're used to one thing, so they continue with that one thing. But there are other factors people consider. Safety is a big one. So for example, if you're going to put in a refrigeration system in a hospital or maybe a school or some sort of public institution, going with ammonia is less attractive, right? Because of the safety concerns associated with ammonia. Certainly cost always plays a big factor, but with cost, the consideration should not just be the one-time cost of purchasing the refrigerant, but the ongoing cost of operating a system using that refrigerant. And then finally, the last thing that really impacts refrigeration system selection and the choice of a refrigerant nowadays is environmental factors. Global warming, ozone depletion, a lot of regulations surrounding those, which goes about impacting how folks select a refrigerant for a system.
Refrigerants are generally sold and transported in DOT cylinders, ton containers, or from an MC-331 tanker trailer. The construction of these containers is designed to withstand some physical impact as well as the vapor pressure of the refrigerant. Refrigerant containers are not designed to withstand the pressure exerted by expanding liquid, which is called hydrostatic expansion. For this reason, cylinders are never filled with more than 80% liquid. The 20% reserve for vapor space provides a necessary buffer if the container is heated and the liquid expands.
You may have heard that no refrigerant container should ever be completely full of liquid refrigerant, and that's true. And that's to avoid what we call hydrostatic expansion. As a refrigerant heats up, it needs to expand. We need room for that. This video is intended to demonstrate where that 80-20 rule that's given in the Rita book, where that comes from. 80% liquid, 20% vapor as a safety factor. And it comes from this. Let's say we have a container and we fill it to 80% with liquid ammonia at a temperature of negative 65 degrees Fahrenheit. It's a very cold refrigerant. It would be filled up like as I've depicted here. All right. It so happens that at negative 65 degrees Fahrenheit, the density of that liquid is 44.11. That's pounds per cubic foot. The reciprocal of density is specific volume. In other words, 1 divided by density is specific volume, which happens to be in this case 0.02267 cubic feet per pound, and that is for that liquid. So that means that 0.2267 cubic feet are needed to hold a single pound of this negative 65 degree Fahrenheit liquid ammonia. Now, something unfortunate happened, and we get a huge source of heat into this container. It's a big Q. This is heat entering the container, causing it to heat up all the way to 125 degrees Fahrenheit. Very substantial temperature increase. But what happens to the ammonia inside there? As it heats up, it's going to affect both the density and the specific volume of the liquid. And I can use the saturation table to determine that the density now has increased at 125. The density has decreased to 34.96 pounds per cubic foot. And this means density's gone down and specific volume is reciprocal, the specific volume's gone up. So that is 0.0286 E cubed per pound. So instead of needing 0.02267 cubic feet to hold our same mass of ammonia, we now need 0.0286 cubic feet per pound. So these two numbers, the difference may not seem that meaningful to you just looking at them, but it actually is pretty substantial on a percentage basis. So if we take a ratio of these two numbers, we take the specific volume at our initial temperature of -65, and we divide that by the temperature, the specific volume, our final temperature, we get a resulting answer of 0.79266. Well, what does that mean? We convert this to a percentage, that's 79.266%. That is where our 80-20 rule comes from. In other words, we filled our container up to the top in this case, and we still haven't experienced hydrostatic, any sort of catastrophic event. 79% of the volume is needed to hold the -65-degree liquid as compared to the 125-degree Fahrenheit liquid. So I suppose it could have been the 79-21 rule, but 80-20 sounds a little better.
A refrigerant container should never be completely filled with liquid because any heat applied will result in extreme pressure increases that may rupture the container. If a container ruptures, the liquid will immediately flash to vapor and could quickly fill a building. Depending on the refrigerant, this could be dangerous to humans, cause a fire, or result in many other negative consequences. A boiling liquid expanding vapor explosion, or BLEVE, is a term applied to any sealed container of liquid that ruptures due to excessive heat, typically caused by a fire. Refrigeration professionals and emergency responders should be aware of the BLEVE potential when responding to a fire at a facility with a refrigeration system. The first refrigeration regulations in the United States were introduced in the 1980s. During the previous decade, scientists became alarmed that CFCs were collecting in the stratosphere. Chlorine molecules from the refrigerants were reacting with the ozone layer, causing it to be depleted. This led to a multinational agreement called the Montreal Protocol, which regulated and eventually banned CFCs. By 1990, 56 countries had signed on to the Montreal Protocol. Around this time, refrigerants began being rated by their ozone depletion potential, or ODP. ODP is a measurement of a material's ability to deplete stratospheric ozone. Refrigerant R11 is the baseline with an ODP of 1. The ODP values for other refrigerants are measured relative to R11. Here are the ODP values for some common refrigerants. The development of HCFCs such as R22 greatly reduced the ODP of refrigerants. Later, HFCs and refrigerant blends were able to remove the ODP concerns altogether. Natural refrigerants such as ammonia and carbon dioxide have zero ozone depletion potential. Global warming potential, or GWP, is another refrigerant characteristic that was introduced in the 1990s. The International Panel on Climate Change, or ICPP, developed global warming potential, or GWP, ratings for refrigerants. The ICPP has adjusted its ratings over the years, but the table here displays the GWPs for the same list of refrigerants. These values were obtained from ICPP's data published in 2013. The Clean Air Act Amendment of 1990 led to further restrictions on refrigerants. The landscape is constantly changing, but in the United States, the manufacture and import of HCFCs is mostly prohibited, and HCFC restrictions are growing. Section 608 of the Clean Air Act required technicians to be certified to handle most synthetic refrigerants. While natural refrigerants are cheered for being environmentally friendly, the Clean Air Act also authorized OSHA to adopt the Process Safety Management, or PSM program, and EPA to enact the Risk Management Program, or RMP. PSM and RMP aim to prevent accidental releases of hazardous chemicals. Compliance with these regulations is arduous, requiring time, money, and expertise to be compliant. To complicate matters, some states have unique regulations for refrigerants. The California Accidental Release Prevention, or CalARP program, is applicable at any facility in California with more than 500 pounds of anhydrous ammonia in a single system. Similarly, the California Air Resources Board has enacted some of the most stringent laws regarding halocarbon use. Nevada's Chemical Accident Prevention Program, or CAPP, must be adhered to at any facility in Nevada with more than 5,000 pounds of ammonia. The regulatory landscape for refrigerants is complex and ever-changing. Refrigeration professionals must remain vigilant to know what is required based on the refrigerant that is used.